After Earth, all known planets in the solar system that come next in terms of size are not terrestrial, as they have a bunch of gas in the form of hydrogen and helium. That's why solar system's terrestrial planets have a density nearly 5 times greater than that of gas-filled planets. So clearly there is a huge difference between the sizes of these two types of planets. But is this the best the universe has to offer in terms of size for terrestrial planets? Can they be much larger, and did we find any that are? The answers to those questions are going to be examined in this video. A planet called PSR J1719-1438b is 4,000 light years away from us, and it has a density of about 23 grams per centimeters cubic, so quadruple that of Earth and about 20 times that of Jupiter. But it also has a mass similar to Jupiter, making it about 330 times more massive than Earth. Its diameter is estimated to be around 4 times that of Earth, so similar to Neptune. Considering the high density, this planet is certainly not a gas giant. And although the density is somewhat in line with that of brown dwarfs, it is also not a brown dwarf either, as it is not even close to the minimum mass for a brown dwarf, which is about 13 times the mass of Jupiter. So despite this planet not being a gas giant or a brown dwarf, calling it terrestrial is a bit misleading. That is because it has an immense surface gravity, many times that of Earth, meaning gases are going to have quite a bit of trouble escaping. The surface pressure could easily be 10,000 times that of Earth, and even that immense atmosphere still wouldn't affect the overall density of the planet such that it is similar to gas giants. Although the indications are that there is a devastating surface pressure, it could still be low enough with a solid surface such that the planet can be considered fully terrestrial. If not now, then maybe it can get there in the future. So this planet orbits a neutron pulsar star at a distance that is only about 2 times greater than the distance of the Moon from Earth, and it completes a full orbit around this neutron star every 2 hours and 10 minutes. It can do that and not be swallowed by the star because it is orbiting a typically sized neutron star, which is estimated to be around 20 kilometers in diameter. And this star also has a mass about 1.4 times that of the Sun. So because of this planet's proximity to this star, it also very likely has an extremely hot surface, meaning the atmospheric molecules are moving at immense speeds, which over long enough periods of time could contribute to significant atmospheric escape. Besides that, it is also possibly receiving intense solar winds due to the close orbital distance, enough such that the atmosphere is constantly getting diminished. However, whether or not the solar wind intensity and very high temperatures can overcome the extremely strong surface gravity, such that the atmosphere is mostly gone, is hard to say. On top of that, this planet maybe also has a magnetic field which could to some extent protect the atmosphere from solar winds. So then maybe this planet is just semi-terrestrial, meaning it could have a solid surface but also be engulfed with an extremely thick atmosphere. However, calling it that also has some potential issues, and that is due to the possibility that the surface is not solid, as it could have a global lava ocean or a global liquid carbon ocean, because the surface is likely extremely hot due to the extremely close distance to the neutron star. Considering the indications showing that this planet is composed primarily of compressed carbon, there is also possibly carbon on the surface. That carbon could then be in a liquid state, considering that carbon starts turning liquid at about 100 bars and 4,200 degrees Celsius according to this phase diagram of carbon. So 1 bar is equal to the surface pressure on Earth. And apparently carbon stays liquid all the way up until about 1 million bars at high enough temperatures. So considering that this planet can easily have an extremely thick atmosphere, and also a sufficiently high surface temperature that could allow for a global liquid carbon ocean to be present, which would then make this planet not even semi-terrestrial due to the lack of solid ground. The researchers that found this planet and released its finding in 2011 estimated the mass of the planet through its orbital characteristics. They also estimated its diameter, and they suggest that this planet is actually the core of a star, probably a white dwarf that lost its outer envelope, and with that, most of its density. That left behind the carbon and oxygen-rich core, and the researchers say that the carbon is crystallized. So yes, there could be plenty of diamonds somewhere in the planet. Kepler-277b and 277c both have a diameter about 3 times that of Earth. Although possibly fully terrestrial, they also have a good chance that they are just semi-terrestrial, meaning there could be solid ground but engulfed in gases with a surface pressure over 10,000 bars. So these two are orbiting a star similar in mass to the Sun but nearly twice the diameter. At the same time, they are both much closer to this star than Mercury is to the Sun. The surface temperature on both of these planets is probably at least similar to Venus, so extremely hot. Possibly there is even a lot more heat, and there could be a global lava ocean. At such a close orbital distance, that also means that the solar winds are probably very intense, so the atmosphere is probably being blown away pretty regularly. However, that still might not be enough such that they are fully terrestrial. That's because there is a good chance that they have strong magnetic fields. Large planets typically have them, so that could shield them to a large extent from solar winds. On top of that, both of these planets have extremely strong surface gravities, so that could also massively prevent the atmosphere from leaving even with very high temperatures. 277b has a surface gravity about 10 times greater than that of Earth, and a mass around 90 times greater than that of Earth, so a similar mass to Saturn. The other planet, 277c, has a surface gravity about 6 times greater than that of Earth, and a mass 60 times greater than that of Earth. Its density of about 9 grams per centimeters cubic is double that of Earth, but also half that of 277b, indicating that this planet is even more likely than 277b to be semi-terrestrial, as the surface pressure could easily exceed 10,000 bars by a lot. So then, are there any planets for which we can say that they are fully terrestrial, like Earth, while at the same time having a diameter a few times greater than Earth? Well, no such planet is known with certainty. But what is known is that the greater the mass of the planet, the harder it is for it to get rid of its atmosphere. And what also correlates with a greater mass is greater size. So the larger a planet is, the less likely it is that it's terrestrial. What one study found is that most planets with a size 1.6 times that of Earth are not rocky, meaning most planets above 20,000 kilometers in diameter are engulfed in gases. Beyond that size, the density of planets found rapidly decreases as they have a sufficient gravity to trap gases to a huge extent. Even light gases which were present in the protoplanetary disk are unable to escape from the extremely strong gravity. There are also, of course, planets stuck in many different stages that are between a gas giant and a terrestrial planet. So then, how do we even know the density of exoplanets? Well, density is just mass divided by volume, so knowing the diameter and mass of a planet also reveals its density. So then, how do we know both the size and mass of an exoplanet? An easy to understand way of finding that out is when an exoplanet is detected through 2 methods, the transit and the wobble method. Transit method is when a planet passes in front of a star, causing it to dim, and through that, the diameter of a planet is revealed. The mass of a planet can be revealed through the wobble method, that is, through the detection of how much a planet tugs on its host star. there are also other ways of finding out what the size and mass of an exoplanet is. Although density can be pretty accurately determined in a lot of cases, that doesn't tell us all that much as to whether or not an exoplanet is engulfed in gases. It really only tells us whether or not it is a gas giant. That's because even an extremely dense planet can still have a devastating surface pressure compared to Earth, and that still wouldn't necessarily influence the overall density such that it is similar to gas giants. As an example, 277b could have an atmospheric pressure at the surface of 10,000 bars, and that atmosphere would only be just somewhere around 0.01% the total mass of the planet, and considering the very strong surface gravity, it also probably shouldn't extend all too much. So knowing the density of a planet does not allow us to accurately distinguish between fully terrestrial and semi-terrestrial planets. So then, in search of fully terrestrial planets, we first have to define what that is. Now, before a precise definition, let's start with an example of something that can certainly be included by the definition, and that is that a planet with no atmosphere or an atmospheric pressure around that of Earth and a solid surface is fully terrestrial. That's pretty easy to agree on. For that, one of the largest planets found so far with an atmosphere, very likely less than 10 bars, is LHS 3844b. With a diameter of 16,500 kilometers, it's quite a bit bigger than Earth. It's also relatively close to us at 48 light-years away. It orbits a red dwarf star at a distance double that of the Moon from Earth, and it completes a full orbit in 11 hours. This planet is tidally locked, meaning one side is always facing away from the host star. And due to the absence of a thick atmosphere, that is why the side which is always facing away has a temperature likely below the freezing point of water. So there it is frigid, while the side always facing the red dwarf star has a temperature estimated to be around 800 degrees Celsius. The reason behind why there is such a large difference between the two sides is because there isn't a sufficiently thick atmosphere to redistribute the heat from the day side to the night side. So this planet is very likely terrestrial, especially on the side at which it is always night. Another one of the largest known planets that likely doesn't have an extremely thick atmosphere is TRAPPIST-1b, which is 40 light-years away from us. This planet has a density almost exactly the same as that of Earth. The conclusions about the lack of an extremely thick atmosphere were drawn from the observation of the planet by the James Webb Telescope, which also revealed the planet as being rather dark. Now, although TRAPPIST-1b has a diameter of 14,200 kilometers, which is not that much bigger than Earth, considering that it likely lacks a significant atmosphere, that is still impressive. The surface temperature is estimated to be around 230 degrees Celsius. So out of all of the mentioned exoplanets in this video, this one overall appears to be the coldest one. So there very likely aren't any lava oceans. The system that this planet is in is also somewhat interesting. It orbits a cool red dwarf star, 10% the diameter and mass of the Sun. It is the closest planet found to the host star in this system, which has a total of 7 planets. TRAPPIST-1b completes a full orbit every 36 hours, and it orbits the red dwarf star at a distance only 4 times further away than the distance of the Moon from Earth. As the study of exoplanets continues, it is likely that eventually even much bigger terrestrial planets are going to be discovered that lack a thick atmosphere. So having solid ground is pretty important for a planet to be considered fully terrestrial. But what is the upper limit in terms of surface pressure for what should be categorized as fully terrestrial? Well, a surface pressure of less than 10,000 bars seems pretty reasonable. So 10,000 bars is 10,000 times greater than the surface pressure on Earth, 100 times greater than the surface pressure on Venus, and 10 times greater than the pressure at the bottom of the Mariana Trench, which is 11 kilometers underwater. This pressure cutoff seems pretty reasonable to differentiate between a fully terrestrial and a semi-terrestrial planet, considering that even Venus, which has a surface pressure of 92 bars, has its atmosphere near the surface in a supercritical fluid state, meaning although it acts like a gas, it also acts quite a bit like a liquid due to the immense pressure. So, if a planet has a pressure more than 100 times the surface pressure of Venus, calling it semi-terrestrial does seem appropriate. The size limit for a fully terrestrial planet isn't known, although beyond 20,000 kilometers in diameter, most planets are not terrestrial. However, there could be some extreme outliers, maybe even fully terrestrial planets the size of Jupiter. If not now, then maybe they are going to exist in the future. But we just don't know for sure whether or not such a thing exists or will exist. The first exoplanet mentioned in this video, the one that orbits a neutron star, appears to have been at some point a white dwarf star that lost most of its outer envelope due to the neutron star taking it away. Planets that formed like that could over long enough time eventually lose the entirety of their atmosphere, leaving behind gigantic, airless, terrestrial planets. So that's one way these huge terrestrial planets could form. Maybe they could also form out of gas giants too. Gas giants have rocky cores. As mentioned, they start off as big rocky planets that then start trapping gases. Jupiter is estimated to have a core quite a bit larger than Earth. The way that a gas giant could then lose its atmosphere is, for example, if it doesn't have a strong magnetic field and then it gets extremely close to its host star. The extreme heating from the proximity then could cause the atmospheric molecules to achieve escape velocity on a great scale, eventually leaving the planet airless. Then a lava ocean would probably be present on the surface, as the exposed surface of the rocky core would be liquid due to the extreme temperatures. However, the orbit of that same planet could then start to slowly move such that it is further and further away from the host star, eventually causing the surface to completely solidify as temperatures drop, which would then create an enormous, fully terrestrial planet. Although this is probably an extremely rare scenario, there is a possibility for it to happen, potentially around a red dwarf star, which can last for many hundreds of millions of years, giving plenty of time for the atmosphere to be stripped away. There is also an example of a known gas giant planet that is estimated to be actively losing a few 100 million kilograms of hydrogen each second, and that is HD 209458b. It orbits its host star so closely that the immense heating causes the atmosphere to extend immensely. That is why, despite it being around 0.7 times the mass of Jupiter, it is also around 1.4 times the diameter. So it is a whole lot less dense as well. However, it probably won't become terrestrial. At this current rate of loss, it is going to need many tens of billions of years to just lose its hydrogen gas content. The heavier gases are probably going to need even more time. And even if that process speeds up, it still likely won't get to become terrestrial. This planet orbits a main sequence star similar to the Sun, and that star will become a red giant in probably a couple of billion years, which will cause the planet to be swallowed because it orbits the host star at only 7 million kilometers, much closer than Mercury is to the Sun. So even massive orbital expansion of the planet won't save it. And if it somehow does lose the atmosphere before being swallowed and destroyed, the surface temperatures that will be present on the surface won't allow for a solid surface to exist. Still, although this isn't a case where a gas giant becomes terrestrial, a scenario was already outlined where such a thing can occur. And although probably extremely rare, it does look like it is possible. There are also probably other ways in which giant terrestrial planets can form. Considering that there is an enormous number of planets in the observable universe, there is quite a good chance that out of those, there is at least one with a diameter a few times greater than that of Earth, and with a solid surface and an atmospheric pressure comparable to Earth, meaning fully terrestrial. Possibly even some the size of Jupiter. If not now, then maybe in the future. However, we can only really speculate about the existence of those planets as of now.